Okay, like to introduce myself. I'm Vicky Messer, one of the Small Cell Forum members of the chair, and also a co-lead on work items. And I work for Ransemi, which is a 4G SoC company. I'm going to chair this session and also introduce the paper. So first of all, I'd like to just give a thanks to the members of the Small Cell Forum NTN Working Group team. The paper was co-authored with Professor Rob Maunder, who's on the session today, and also co-led by Prabhakar, who's the Small Cell Forum chair. And we've got contributors as listed here, and we're happy to have some representatives, key contributors on the session today. And finally, we're going to have a questions and answers session at the end for 10 minutes. So please put your questions in the question and answer section, and we'll run through them at the end. So why are Small Cell Forum interested in NTN? Well, there's been a lot of interest in NTN recently, and the team got together, and there was definitely interest in working on a work item and producing a paper. And what was seen, although there are differences in terms of small cells having small coverage and small capacity compared to NTN, which is a very large coverage area, there are some key constraints and product parallels which are worth identifying, which have the same challenges that you do with small cells. And one of those is the size, weight, and power constraints, particularly when you've got a GNOB sitting on the payload on the satellite. There's also standardized for 5G NR, there's standardized interfaces that can be reused. And then some of the topics that Small Cell Forum are involved with, such as spectrum sharing and neutral host and shared networks, also can be applied. So the paper focus, which was published in December, the end of last year, focuses around the regenerative 5G NTN solutions and architectures. There are other implementations at the moment, and we'll touch on those. But the regenerative are where we're sort of focusing, because that's where a lot of the challenges are and where the technology needs developing further. So looking at the network elements that are also on the LEO, the low Earth orbit satellite, so focusing on that and keeping the scope to the 5G RAN and core network. Also looking at the applicable standardized interfaces, which are the ones that make sense for those use cases. Looking, and I'm going to cover a little bit of this in a minute, at what the requirements are for space grade components, given the experience of the industry, and whether you can use common off-the-shelf parts in these applications, say on a low Earth orbit. We're also going to be covering, it covers beamforming and handovers, and we're getting some more information around that from Ganesh, and also looking at use cases. So I'm going to just very briefly look at the different architectures, specifically for regenerative NTN. This is where some or all of the GNOB resides on the satellite, compared to transparent, which Ganesh is going to talk about in his case study. So there's three key ones that are all specified by 3GPP. And one is known as partial regenerative. So it uses the split 2 architecture where we're using the F1 interface defined by 3GPP, and you have the CU on the ground station, and then there's the DU and the RU, and the beamforming technology is on the satellite. Then in fully regenerative, the full GNOB, including the CU, is on the satellite. And then it uses the 3GPP defined NG interface to talk to the ground station and the core network. And then there's also the option of, and there's certain use cases which may benefit from this, where the part of the 5G core sits on, which is the user plane function, sits on the satellite alongside the GNOB. So these are discussed in the paper. This is a generic, it's a modified version of an product architecture that we've done on previous papers. It's been drawn out specifically for NTN. So just to highlight a few things on here. So we've got the FAPI interface between the NPU and the layer 1, 2, 3, and the layer 2 physical layer. So this is the FAPI that's defined and within the small cell forum team. And we're looking at updating that to include NTN. The other areas to point out is there's an optional digital beamformer within the baseband before the baseband gets converted to RF. But there's also an optional beamformer in the analog mode. And then also for NTN, it could be FR1 or it could be FR2, so a millimeter wave. So we'll hear more from Garçon about the millimeter wave application of that. So just one thing to talk about space components and the conditions that those components are subjected to, the environmental conditions, and what the source of those conditions are, and also any mitigation or any standards. So generally, terrestrial off-the-shelf devices or terrestrial devices are qualified under the JEDEC JST22 standards. However, as the paper details, the space environmental conditions present additional risks. And there are additional qualification screening that can be done. So you could use standard terrestrial devices, or maybe industrial or automotive devices, and do some extra screening. And a benchmark of the NXP LX2160 space has been supplied through Teledyne. And that sets a benchmarking for other components. And this includes Ransemi's own RNSA22 4G, 5G, PHY SoC. And there are space standards defined by NASA and the EU, which goes into this in more detail. So now I'm going to introduce you Rob, who's going to, from Accelercom, and he's going to take you through his section of the presentation.
Thank you, Vicky. And hello, everybody. It's my pleasure to be here with you. And thanks again to Vicky for her leadership in this this work item in Small Cell Forum. I'm the founder and the CTO of Accelercom. And in this part of the webinar, I'll talk you through a few different areas. I'll start by looking at different use cases for NTN. Then I'll give a bit of an introduction to beamforming and the impact that has on the architecture of a payload for the regenerative NTN satellite. And then I'll give you a case study around how at Excelicom, we are using the FAPI interface, which Vicky mentioned just earlier, as the basis for a test environment that we use to prove our layer one in isolation from the rest of the system. So let me begin, first of all, by introducing Excelicom and explaining what it is that we do. As Vicky described, 5G standards for non-terrestrial networks are enabling satellites to have connectivity to a much wider variety of user devices than previous waveforms have allowed. Where those previous waveforms have been proprietary or customized in some ways to suit the needs of particular satellite constellations, 5G is a standard which is adopted not only by satellites and ground stations, but by a wide variety of user devices. And in the following slide, I'll take you through a variety of different types of user device. In a regenerative architecture, the 5G base station sits on the satellite, and that has various different advantages in terms of performance and resilience for the network. But there are some challenges in implementing such a system. So first of all, as Vicky explained, the components that are used on the satellite have to be low power, they have to be radiation tolerant. So the onboard processor is constrained in size, weight, and power, and space qualification. And then running on those components, those processor devices, needed is various parts of a 5G base station. So the layer one is the particular focus of Excelicom. And this comprises hardware components, perhaps running in FPGA or AI accelerators, as well as software and interfaces, standardized interfaces, such as the small cell forum FAPI interface. And then also on the satellite is the rest of the 5G stack, the layer 2 and the layer 3. And Ganesh from Radisys will talk more about this in a following part of this webinar. And then there's antenna arrays and so on that go on the satellite payload. So the key part that Excelicom is offering is that layer one software, the layer one firmware, and having it work specifically on the sorts of devices that can be put onto a satellite. And this is in contrast to 5G base stations that are used in terrestrial networks that typically exploit x86 server chips or ASICs that are not designed to go into space. Let me talk now about some of the use cases. And the use cases for NTN can be categorized in a number of different ways. One of them is the user terminal type. And so on this table here, you can see a variety of different types of user terminal, and they are ordered according to their capability. And as their capability is increasing, then their cost and their power requirements are increasing as well. But the most capable among these, sat at the top of the table, is a very small aperture terminal, a VSAT terminal type. So you can imagine a antenna array that you might put on the roof of your house that gives broadband connectivity to satellites overhead. Next type of terminal here is a vehicle terminal. This may also be an active antenna array, allowing its directionality to be steered towards the satellite as it moves through the sky. Of course, as a vehicle terminal, it will be connected to a vehicle, and so it's mobile in that regard. The next step down from there is a handheld terminal. So it could be a smartphone, for example, using direct-to-device aspects of non-terrestrial networks. And these may be battery operated. They will typically have an omnidirectional antenna, which presents some challenges for the satellite, having to be more capable in order to deliver power sufficient for these terminals to receive those signals. And then the least capable would be an Internet of Things terminal. Typically, these may have to run on limited battery power for long periods of time. So again, there are challenges moved from the terminal onto the satellite. And broadly speaking, the more capable the user terminal is, the less capable the satellite has to be, and vice versa. So what we see is that satellites for direct-to-device applications have bigger power requirements. They're perhaps bigger satellites than those for broadband VSAT kind of applications. Another way that we can categorize the use cases is through the application. And there are a number of different applications that are listed here. Typically, we can expect non-terrestrial networks to be complementary to existing terrestrial networks rather than a replacement for those networks. And so the applications tend to be things besides coverage for dense urban areas. So one particular aspect is rural and remote coverage extension, and there can be direct-to-device connectivity to smartphones, for example. There can be broadband connectivity to VSAT terminals in that case. Other examples are mission-critical or emergency communications, giving resilience to failing terrestrial networks in the case of emergency, And again, it could be direct-to-device use cases. It could be broadband coverage as well. There's transport and automotive applications where vehicles leave populated areas and need continuous coverage. So again, these can be vehicle terminals. It could also be VSAT applications again. And then the Internet of Things use cases, you can find those in enterprise, industrial, agricultural kind of applications. Let me now introduce beamforming. I'll start off on this subject. Colleagues from Radisys and Microsemi will elaborate further on this as well. But I'll just start us off. So we can see here an image of a pair of satellites moving through the sky and projecting beams onto the surface of the Earth, creating cells of geographical area of coverage. And there's a variety of different ways that this can work, which Ganesh will elaborate later on. But one way is a Earth-fixed configuration where the cells stay stationary, and it's the satellites that angle their beams as they move in order to maintain that coverage. And as you can see, as one satellite moves away and another satellite moves into place, then it will take over the service of some of the cells from that first satellite over time. And it may be that beam hopping techniques are used. It may be that not all of the beams are active all of the time, and that instead different subsets of the beams are activated in order to allow power to be concentrated into them and to avoid interbeam interference. So for example, it may be that at a particular moment in time, it's the green colored cells here that are active, and at other times it may be the blue or the salmon colored beams that are active. And so what we can see is that beamforming in non-terrestrial networks is performed on a per cell basis rather than on a per user basis. And this is in contrast to terrestrial networks, where in fact the beamforming is typically performed on a per user basis. Each individual user is maybe having a beam directed directly at it, whereas in NTN, it's the coverage of an entire cell that's being formed. And here the beamforming is driven by the relative positions of the satellite and the fixed cell, rather than on the multipath environment, the channel conditions between particular users and the base station, okay, as it is in terrestrial networks. And that has some implications for the architecture of the payload. And so as we can see, because the beamforming is performed on a per cell basis, and because it's not dependent on any channel condition information that's available inside the physical layer of the 5G base station, the GNOB, this means that the beamforming can be performed instead in the time domain and outside of the physical layer of the GNOB. Again, this is in contrast to terrestrial networks, where typically the beamforming is performed in the frequency domain inside the phi L1. And so this has some implications for how we may architect the payload of an NTN system. It may be that the number of beams, that the capacity of a satellite is very, very high, and that multiple processors are needed to perform all of the signal processing for all of those beams. So in the diagram you can see here, there are multiple parallel L1s and multiple parallel L2s, which are providing service to different subsets of the beams. And again, in a beam hopping environment, it may be that different beams are active at different times and being serviced by different ones of these processors. And that you can see there's a dotted line there showing where the small cell forum NFAPI interface resides. But with an architecture like this, there can be a single digital beamformer, or maybe it's an analog beamformer, or maybe it's both in a hybrid beamforming system, but a single beamformer IC that's combining all of the different signals from all of the different processor chips. And so again, this is another motivation for having the beamformer outside of the layer 1, in that it allows multiple L1s to be connected together into a single beamformer. And then the control of that beamformer can come from externally to the base station, because there's no dependence on channel conditions that are available inside the layer 1, for example. So in the diagram you can see here, the beam controller is providing beam weights and phase shifts directly to that digital and analog beamformer, rather than having that control information coming through the GNOB through the layer 1. And an advantage of this is it allows satellite network operators to inject their own secret sauce, their own value add into the design of that beam controller without it having to be tightly integrated inside the GNOB, which often they'll be sourcing from other suppliers. There is one aspect though where there is tight integration needed between the beam controller and the scheduler of the layer 2, these things have to be coordinated. There'll be certain periodic signals that the layer 2 would like to schedule, but it has to impose a constraint on the beam controller to make sure that those beams are active at those times in order that those periodic signals can be scheduled. And likewise, the beam controller puts constraints on the MAC scheduler. If a beam is disabled at a certain time, then the MAC scheduler needs to know about that so that it doesn't schedule things in those slots. So let me talk a little bit now about a case study for how Accelercom is using the NFAPI standard as the basis of a test environment for the layer 1 software and firmware that we develop at Accelercom. You can see a diagram here which shows how we have a test environment that comprises our layer 1 running on development boards connected into test equipment. And because we have the layer 1 isolated from the rest of the G-Node B, it means that the test equipment does not behave as a fully functional user equipment, but instead we use a signal analyzer and a signal generator. And the benefit here of testing layer 1 in isolation from the rest of the system is it allows a really thorough exploration of all the different corner cases, all the different steps in all the different procedures of the 5G standards very exhaustively and very thoroughly. So for example, there's a UE attach process where a user equipment will connect to a base station, and there's several steps in that process. But with this test environment, we can pick out one of those steps and just run it over and over again in all sorts of different configurations, different block lengths, different coding rates, different modulation orders, different options on all the different parameters of those, and test that we're getting the performance that we see in our simulations. We can test that we have the conformance with the 5G standards, and we can test that we have the capacity to process all of these different signals in parallel across many beams and many users. And so to coordinate all of this, we have developed software which we call TestMac. And TestMac coordinates the operation of the layer 1 through the NFAPI protocol in exactly the same way that a layer 2 would orchestrate the operation of layer 1, but where the layer 2 is taking the layer 1 through all the different steps of all the different processes. Instead, TestMac can just direct layer 1 into any step of any process at random in any order it prefers. And the TestMac software then uses a Skippy protocol to control the signal analyzer and signal generator as well, so that a particular test can be set up, and so that the signal generator, for example, is generating the signal that the layer 1 is being told to receive and demodulate. And likewise, the signal analyzer can be set up to receive the signal that the layer 1 is being instructed to generate by the TestMac over NFAPI. So I'd like to conclude here. I'll pass over to Ganesh at Radisys, who will take us through the next part.
Yeah. So my name is Ganesh Shanbharaman from Radisys, and I take care of the standardization activities. My team has contributed to this NTN white paper, so happy to talk about this with the fellow panelists here. And Radisys, we supply the RAN software and the core network software as well. And let me just move to the next slide. So this is the Radisys NTN solution. Just to give you a quick overview of our role in this segment. We have been a RAN software provider for 3 decades, close to 3 decades, and with the heritage of supplying 3G, 4G, 5G small cell software as a pioneer. So the same software is being used and adapted for the NTN deployments, and we do this for both the transparent architecture and the regenerative architecture. And what you see here is an end-to-end picture of the Radisys software capabilities when it comes to NTN capabilities. So right from the base station of the G-Node B, which needs to be adapted for the small weight and power constraints. So we need to optimize the layer 2, layer 3 software to fit into those footprint requirements, both in terms of compute memory and the power utilization. So we do that, and we have successfully done this on multiple platforms. And we also make a very heavy use of the FAPI and FAPI protocols defined in Small Cell Forum to integrate with multiple 5-layer providers, and that includes Accelercom, Rob, Steam in this case. So we do this integration using the FAPI or NFAPI interface, and we also adapt the layer 2, layer 3 software functionality in terms of the 3GPP specs, which are defined prior to 5G. There was not much of a standard available. There were some proprietary implementation. Now in 5G NR, the 3GPP release 17 onwards, we have several features defined, several adaptations defined in the 3GPP specification for the G node B to communicate with the standard 5G UE. So talking about the UE, we also have the software stack for the UE side, and again, integrating with the different layer one and stuff. And to give the end-to-end capability, along with the Radisys NTN capable 5G core network, which is again a small footprint implementation from Radisys to fit into some smaller footprint platform. And in some cases, it could be a portion of the 5G core network that there may be a desire to host that part, let's say the user plane function on the satellite platform or the device that is on the satellite. So all of this is done with a view to optimize power and memory utilization and so on. So we do this in a unified fashion. The implementation is capable of translating or scaling it well across the GEO, MEO, or LEO constellations. And we are release 18 compliant today, and we will be upgrading to release 19 capabilities to support the full regenerative capability in NTN. So this is a play for us in partnership with multiple ecosystem partners, providing layer one, the control part of the beamforming and max scheduling and other things, and also several SoC or hardware platform providers. I'm moving on to the next slide. So we talked extensively about beam coverage, and thanks, Rob, for the detailed explanation. So the aspect we want to talk about how this impacts the mobility part of it. So like Rob explained, we tend to conserve the number of beams that are eliminated based on the area of coverage. And again, the selection of which beams are eliminated is based on several considerations, including the area covered and the areas where or the uses where traffic is located. So that logic is explained a little more in detail in the next slide as well. So assuming a select number of beams are active in a coverage area, the tracking areas assigned, the tracking area IDs assigned to each of these cells. And how do you handle both the static and moving devices? The mobility aspects of it is an implementation detail, basically the layer 3, layer 2 implementation, how to accommodate for this the types of beams which we are using, the earth fixed beams or the earth moving cellular beam and the quasi earth fixed beams. The handover mechanism will also be dependent on whether it is a transparent architecture or a regenerative architecture. So all these implementation details, again, you will find some mention in the white paper, but a more detailed explanation will be available. If you are interested, please contact me. And I'm moving to the next slide, which is the beam hopping and scheduling part. And the beam hopping aspect is the dynamic allocation of the satellite beams. And again, as per the service demand and the traffic demands. So there is a complex or a sophisticated mechanism that is required to schedule or hop the beams across a time slot just to service the users with the select or the limited number of beams available. And again, this is in view of conserving the overall power consumed. So we will reuse some of these spot beams, and spot beams meaning the satellite beams. And we also have to consider the mobility management aspects of the devices and all the service KPIs or the QoS requirements that have to be met for each of the users connected will also be considered in beam hopping. And while we do all of these things, there are specific challenges in the NTN case for the uplink to maintain the timing advance and the appropriate UE power control. So with all these constraints implemented in, let's say, in coordination between beam hopper and the MAC scheduler, the scheduler which I'm talking about is the MAC layer scheduler. The MAC layer scheduler has to very tightly interwork with the beamforming scheduler to provide appropriate resources. And again, one of the challenges in the layer 2, especially here, is that the number of beams or the number of cells which we are talking about, the MAC layer scheduler has to be capable and intelligent to scale it across this increased number of beams or cells and provide adequate bandwidth to each of the users. And given that there is a bandwidth limitation as well in NTN, unlike the terrestrial network case, we have to be the scheduler has to be very intelligent to schedule appropriate amount of traffic for each of the connected users. And again, there is the intelligence aspect and the dynamic control aspect of the scheduler. And that makes it more challenging to have real-time performance of layer 2 scheduler, and of course the layer 3 aspects of mobility management and everything. Okay. And I also want to talk about a use case. Quickly about the FAPI enhancements. This is a work item that is happening right now. Release 11 is work is going on. The definition is going on. Several topics are planned to be covered related to NTN. There are some non-NTN topics as well in release 11 FAPI work. If you are interested, please join those working group discussions. So beam hopping, handover support, and the Doppler compensation, the beam forming control, all these topics are covered in the release 11, and this is an ongoing work for NTN support in a detailed manner in our FAPI specification. So please take a look at that. And the final slide on the case study. So this is one major customer we have in the North American region. We have built the 5GNR transparent NTN solution, and this involves all the integration on the target SoC platform, hardware platform, and it's the transparent solution. So the GNODB is not in the space. And we have successfully integrated this solution on a live network of geo satellite configuration from Intelsat, and this is the Intelsat Galaxy 19 configuration which we are talking about. So we've been able to show a successful end-to-end connectivity and traffic with this solution, our solution hosted for the transparent architecture, along with the real devices and test equipment, and make sure that this is working end-to-end. And this will be an ongoing work for us, and done some specific customizations to provide a very secure NTN GNODB. And we are also in the progression to implement more advanced features and bring in the advanced capabilities of release 18 and 19 for this customer. So this is an example, and we have several other examples of multiple customers trying fully regenerative and across regions, North American region, European region, and other places as well. So we continue to work with our partners in ecosystem, partners in the ecosystem for the integration and the end-to-end deployment. And thank you for this opportunity. And I'm turning this over to Marcin now.
Okay, hello everyone. I'm Marcin Guralczyk. I'm a CTO at Micramp, and I'm happy to talk about 5G millimeter wave in terms of NTN, especially on the beamforming, and present our case study that we presented in the paper. So about Micramp, we are a global leader in 5G millimeter wave technology, and we have a fully 3GPP compliant solution, which we started by building our own purpose-built radios, millimeter wave radios, based on our IP. But since the very beginning, we took the end-to-end approach, which means that we provide to our customers not only the hardware or software, we provide them full end-to-end solution, which consists of the radios and devices like CPEs, user equipment, network software, core network, and what is even more important, we provide them use cases, the real use cases that they can start working on, implement in their to solve their issues that they have with other technologies. So currently Micramp is in Micramp more than 40 people are involved globally. We are a EU startup headquartered in Warsaw, Poland, and we have more than 40 deployments all over the world in 17 countries already, starting in Far East like Japan, through the whole Asia, Europe, like Germany, France, UK, Ireland, and even in the US. So we have deployments in various sectors, in academia, industry, government, defense, and also space. As a company, we're focused on millimeter wave here. I will also focus on the millimeter wave works in the NTN space. So basically, the NTN and specifically millimeter wave are trying to cover or address key challenges in the global communication, which is a limited coverage, where of course, like more of the most of the land and sea is not covered with the coverage, and there is always demand for always available connectivity, especially for the emergency services or industry and IoT devices, which need reliable coverage in all the areas. And also the main issue with the legacy satellite limitations, which is high cost and that they use low bandwidth and proprietary solution. So what millimeter wave can bring here is basically the capacity, the bandwidth that you have available in millimeter wave is enormous compared to any other lower frequencies. And so capacity and the ultra fast connectivity. These are the main features of the millimeter wave in NTN. Other are, let's say, shared with other NTN networks, so like enhanced resilience and redundancy, so as a backup or overlay to the terrestrial networks, and also cost efficiency in various environments where developing terrestrial infrastructure might not be cost efficient. Then bringing the space-based infrastructure gives you a possibility to have a connectivity at all. And of course, it's strategic and economic impact with a reduced digital divide and accelerated network deployments in emerging markets and also new commercial and defense applications. So our focus in the paper itself was on the beamforming and how it compares in the NTN millimeter wave and the terrestrial deployments. So if we look through the regular deployments of the millimeter wave on the ground, usually these are like either fixed wireless access like deployments or mobile deployments where the user is moving. In fixed wireless access, you use CPEs, customer premises equipment, which is static. Then you have a like point-to-multipoint type of communication, and you don't need dynamic beamforming at all. In such cases, you can rely on the static beams. But in a mobile scenario where the user is moving around, like with the smartphone, then you have a fast changing environment. So you need a continuous low latency feedback to adjust the beam, to switch the beam when the user is moving. Because the physics of millimeter wave is that you have to keep the good signal quality, you need to have a very directional beam. You need to use large antenna arrays. And large antenna array means that you have very narrow beam. So to keep the coverage, you need to steer the beam in millimeter wave. And so this is the, let's say, main challenge with the millimeter wave, to keep the user connected when it's moving. And if we compare the NTN deployment, you have a orbit, the satellite on the orbit is moving on the predefined orbit. So you know where it is in every time. And also, while the absolute speed might be high, the angular frequency is relatively low. So the managing beam in such case is much easier compared to the terrestrial network. So you don't, and also key thing here is that you cannot rely on the feedback from the CPE, for example, to the base station, because the delay is too high. So effectively, you use open loop feedback here to control the beam. Also, in the terrestrial deployments, usually you have a lot of users connected to each G-node B, and each user can use different beam, which means that you have to control the beam on a per each UE, and which means in every slot or even every symbol, you might need to switch the beam. While in NTN, of course, it depends on the architecture of the whole network, but usually it's like a frame level or longer, the time scale of beamforming for this. So the beamforming driver in the terrestrial networks is instantaneous channel state, while on the satellite it's orbital inference and coverage geometry. So the nature is fully adaptive in terrestrial, while on the satellite it's static or semi-static. The key differentiator here, however, is the Doppler effect. On the ground, the speed of the user is relatively slow, while on the satellite, still user is not moving that fast, but the G-node B is moving fast. So you need to take care of the Doppler effect. But again, on the satellite, it is rather deterministic. So by design of the network, you can take care of the Doppler effect itself. And also the holy grail of the whole NTN networks is to use user devices that are already being used by people, which means the perfect case would be that you take your smartphone and you connect to the satellite, and you have coverage everywhere. So this is the so-called holy grail for the NTN. And in terms of FR2, all the user equipment is used at the moment support only TDD, while the 3GPP standard at the moment predicts only FDD deployments. So how to work on it is not easy. So we are trying to address this together with European Space Agency. So as a first step, we together with them, we deployed a 5G millimeter wave network, of course on the ground, but with the NTN backhaul. So as you can see in the diagram here, so we have our G-node B deployed in our office, and CP is connected to it. And then we have a remote core network in Harwell in ESA 5G 6G hub, connected through the VSAT terminal. Namely, it was Starlink used in this exercise, and we connected the full backhaul, so end-to-end 3 interfaces through the Starlink. And we compared how the system performance in terrestrial and with the NTN backhaul. So in that case, we use the FR2 N257 band. So the setup was working on 27.6 gigahertz with 400 megahertz channel. We use Hyper-3 for the throughput testing. And as mentioned, it was the Starlink use, so LEO constellation, where we connected a backhaul through it. And so as we see here, the main limitation here currently is the NTN backhaul, which puts the main constraints on the total performance, but still the performance achieved was very, very good, since we achieved around 270 megabits in downlink and 45 megabits per second in uplink, while the round-trip time latency was below 23 milliseconds, which means that one-way delay using satellite backhaul was around 11-12 milliseconds, which is even sometimes not achievable for the terrestrial sub-6 networks. So as mentioned, currently there is no FDD end devices for the 5G millimeter wave. So there are some works to validate if using TDD and in NTN makes sense, because the main logic behind this would be to use current end devices for the NTN communication. And this is also the work that we are doing as a next step. So to design and deploy the fully regenerative and 5G payload, 5G millimeter wave payload, with the goal to connect through the satellite as a feeder link. No, as a service link, sorry. And that's it. Thank you very much.
Thank you, Marcin, and thank you for all the other presenters as well. And thank you for everyone's questions coming in. So we've now got some time, we're pretty well on time, to do a Q&A session. So I've got some questions that have come in, and panelists, please jump in if I've not sent them to the right person. So I think I'll come to the first question. Okay, so in NTN systems, how do you optimize beamforming to account for dynamic and unpredictable nature of satellite movement and atmospheric conditions? So maybe start with Rob on that one.
Okay, thank you. I think I would make the argument here that actually the satellite movement is very predictable, and that there's a lot of mechanisms using GNSS systems, for example, for a satellite to know exactly where it is. It's on a predefined orbit. It's relatively straightforward to predict where it's going to be. So I would make the suggestion that actually the satellite movement isn't unpredictable. The atmospheric conditions, I would suggest that the state of the art here is to assume that the atmospheric conditions are not having a big impact on how the beamforming has to be performed and how the beams will be cast onto the surface of the Earth. As I described before, the state of the art is to perform the beamforming in the time domain without access to channel state information. In the future, what we may see is a bending of that and more of the, or some of the processing happening in the frequency domain with knowledge of channel state information. And in those circumstances, the atmospheric conditions, also multipath effects, if a user happens to be in a reflective environment, could be considered. But I would suggest that that's not the state of the art today.
Thank you. And Ganesh, can you come off mute and maybe comment on the dynamic nature of beamforming on that question?
Okay, I think the same question which Rob answered, right?
Yes.
Yeah. So I think Rob, when he concluded, he talked about this channel state condition and other things, which is not considered right now. So the beamforming happens in a predictable fashion as per the navigation, which is predictable. And again, the atmospheric conditions do not affect as well. But seen from a UE or the user perspective, we may not be able to give the same guarantees as the terrestrial network. And again, that's because of the way currently the state of the technology is. And again, there's not really best effort, but there are some coverage challenges, let's say, based on where the user is, which is not really related to the atmospheric conditions. It's about whether he's able to receive the satellite signals or not, depending on the location, foliage, and other factors which might interfere with the coverage, even if this beam is eliminating that area. That could be the challenge from a user point of view. And again, from a base station implementation point of view, we also look at the lack of such feedback and other things when we are scheduling usage. So there is some amount of intelligence which we can build in our scheduler and based on the beamforming that is decided. But the equivalence, or I would say the level of implementation cannot be the same as what we have for terrestrial network in summary.
Okay, thank you very much. So Marcin, you and Microamp have been working on millimeter wave both on terrestrial and non-terrestrial. How does it compare in terms of power efficiency and coverage?
In terms how the millimeter wave deployment compares to the NTN compares to terrestrial, right?
Yeah, both millimeter wave. Yeah.
Both millimeter. It's not easy to answer since there is no real 5G millimeter wave NTN deployment yet, right? So we are working on it. So it's not yet deployed. Of course, the main in terms of power efficiency, key here is the antenna gain and this basically the link budget here, and how big the cell will be. The key thing with the millimeter wave is that it's we use very large bandwidth here, so it's like 800 megahertz, and so which means that effectively we have to use analog beamforming, because for digital beamforming you need to compute each channel separately. So imagine if you have antenna array of, I don't know, let's say even 128 elements, each with 800 megahertz and digital processing. This will give you so much need for computing that it's impractical. It's impractical on Earth, and it will be even more impractical in space. So effectively, for the millimeter wave 5G, we use analog beamforming, which is much easier to be processed and to predict how it works. Of course, the drawback of this is to some extent limited precision of steering the beam. But still, because of the amount of bandwidth, this is how it's done in practice now.
Very good, thank you. And yes, so Marcin and Microamp contributed on the millimeter wave paper, and there's more details about analog beamforming in that as well. A question for Rob. Can you explain the power efficiency, latency capacity, and other advantages of regenerative versus transparent architectures?
Yeah, there's a variety of different advantages of regenerative compared to transparent. The big challenge of regenerative is, the need to put all of that signal processing onto the satellite, but that's the challenge that we're addressing. In terms of the advantages, one of the key ones is indeed in terms of latency. So if you consider the process for transmitting some information from a user terminal into the network, there can be lots of back and forth between the user terminal and the G-node B, and this is called the HARC mechanism. In general, we try to avoid this in non-terrestrial networks because of the latency that I'm about to describe, but nonetheless, it remains there as a key piece that imposes the worst case latency on the system. And that is that when the G-node B is on the ground, then that back and forth, the sort of retransmission attempts have to go up and down several times from user terminal to satellite to G-node B and back again, adding up to a big latency. Whereas if the G-node B is on the satellite, then that back and forth is only happening on the feeder link. And typically the distance from the user terminal to the satellite can be smaller than the distance from the satellite to the ground station. And so there's a big latency advantage. Other aspects are that decisions that are made by the G-node B is based on more up-to-date information because it's closer to the user devices and to the channel. And so that can lead to better use of resources. It can lead to better spectral efficiency, better link budget closure. And then other aspects are that there can be losses in the feeder link, particularly if, for example, in a direct-to-device use case, you may be using FR1 for the service link, but FR2 for the feeder link, because the feeder link needs a wide bandwidth to bring in all the different signals of all the different beams. But the waveform has to be common between both, because in transparent you're just relaying that same waveform. And so you have a challenge then of, do you optimize the waveform for FR1 used in the service link, or do you optimize it for FR2 used in the feeder link? And that can lead to compromise, and that can lead to losses. So these are a quick snapshot of some of the different advantages and disadvantages. Actually, I've given a webinar on this topic in the past, and perhaps what I'll do is in the chat here, I'll post a link to that for you if you're interested in following up.
Thank you, Rob. So Ganesh, just there's a question around computational overhead, particularly with the large footprints, large beam footprints. Can you just comment a little bit about that, the NPU processors needed in regenerative?
Sure. Yeah. So this is the area for a software vendor like us to further work on or optimize the implementation. And obviously there is a challenge of the total compute available, the power consumption limits, right? And so the equivalence or the relevance of a small cell implementation in an NTN extending that a little bit more because the number of cells or beams which we need to handle here is much more than a typical small cell implementation. So there is obviously a stretch on the implementation in terms of the number of cells or beams to be addressed in the layer 3 and layer 2 aspects, plus the appropriate logic to be implemented, the additional compute logic for NTN, including the beam hopping aspects. So there is obviously a challenge of optimized implementation, both from a memory and compute point of view. And this is what we've been working on in optimizing our software around the constraint platforms, which are typically, let's say, an ARM-based processor in this case. And we do several techniques to optimize the software to limit the usage and handle multiple UE contexts and cells and beams and the logic of scheduling, right? And so we've been able to manage this for both the transparent architecture, partial regenerative, and finally the regenerative architecture. And we are also able to optimize our core network footprint as well, at least to accommodate the user plane. In some cases, some use cases, we have seen the requirement to accommodate the user plane function of the 5G core network. So it's all doable, and we have done it in specific use cases and customer deployments. And again, we keep close track of the evolution of the improvements in the hardware architecture. As we gain access to more newer and innovative platforms, we make use of that capability to shrink it further.
Thank you very much, Ganesh. So once again, thank you to all the presenters and for your questions. The recording link will be shared with all the participants who've signed up, and the presenters' email addresses are here as well. So if you had any further questions, please get in touch. So once again, thank you very much for joining.